Underneath the sleek exterior of every modern EV, there is this high-stakes, literally invisible battle happening every single millisecond. We're talking about microscopic physical forces constantly colliding with immense electrical power, right inside the powertrain. In today's Explainer, we're diving straight into one of the absolute most critical safety threats in the entire EV engineering world, the BMS limit conflict. We're going to break down exactly how it triggers, how it's diagnosed on the fly, and the absolute fortress of engineering built just to prevent it. Now, to really grasp the gravity of this, we've got to talk about ASIL D. As most of you know, this is the absolute highest, most stringent functional safety classification in the automotive industry. A BMS limit conflict is not just some quirky software bug. If the powertrain and the battery management system lose their synchronization during, say, high-speed traction or heavy regen braking, the results are catastrophic. We're looking at unintended acceleration, severe battery overcharge from reversed energy, or just a total sudden loss of torque. It is essentially the ultimate worst-case scenario. So how does the vehicle normally keep this chaos in check? Well, think of the battery management system, or BMS, as the ultimate traffic cop for the EV's powertrain. It is constantly crunching data on cell temperature, state of charge, battery health, and it uses all that to calculate strict dynamic speed limits. You know these as the charge power limit, or CPL, and the discharge power limit, or DPL. These limits dictate precisely how much power those dual-motor inverters are allowed to pull from or push back into the battery pack. And if the motors ignore those strict boundaries, bam, we've got a conflict. Here is our roadmap for today's Explainer. We'll hit fault root cause analysis, architecture and diagnostics, DFMEA key design prevention, PFMEA key process controls, and finally, DVPNR production validation. Let's get into it. Section 1. Fault root cause analysis. Let's investigate those invisible physical forces. Okay, so a single system failure here can actually originate from 4 totally different physical dimensions. First up, we've got extreme electromagnetic interference just completely scrambling the communication network. Second, when motors are pushed to their absolute limits, their magnetic fields distort. That's deep inductance saturation, which causes the mathematical models to straight up fail. Third, we have software timing quirks, where critical safety tasks basically get stuck in line behind heavy motor calculations. And fourth, physical wear and tear on the bus bars can create a false voltage reading, tricking the entire system into thinking it's safe when it's definitely not. Let's zoom in on that first dimension for a second. Inside these high-density power enclosures, silicon carbide MOSFETs are switching at incredibly high frequencies. This generates some massive voltage transients. We're talking about a change in voltage over time, or DVDT, of 10 kilovolts per microsecond or more. That is a massive wave of electromagnetic noise injecting strong common mode interference right into our low-voltage CAN lines. And if the network loses frames because of this physical noise, the motor controller is forced to rely on old, outdated power limits. It's literally driving blindfolded at 100 miles an hour. And that leads us to the software side of the threat, which is beautifully illustrated by priority inversion. See, motor control algorithms run on hyper-fast 100 microsecond timers, right? They need those instant reactions to keep the wheels turning smoothly. But the BMS limits? Those are usually unpacked in much slower 10 millisecond tasks. So if the processor gets overwhelmed, those heavy motor calculations actually block the system from receiving the new restricted power limits from the BMS. The timing disconnects entirely, and the motor just keeps pulling massive power right at the exact moment the battery is desperately trying to tell it to stop. Moving to Section 2, Architecture and Diagnostics. This is a real-time security system. The primary defense here relies on a heterogeneous, dual-core, lockstep architecture. The microchip is literally split in two. Over on the left, we've got the doer. That's the main core handling all the heavy lifting, calculating the precise torque and current for driving. Over on the right is the checker. Now, the checker doesn't just repeat the math. Instead, it uses simplified physics models to constantly audit the doer. If the checker detects that the doer's commands are going to violently break the BMS limits, it bypasses the software entirely and physically cuts the power in less than 100 microseconds. No questions asked. And that speed? It's completely non-negotiable, all because of the ASIL D fault-tolerant time interval, or FTTI. From the exact millisecond a fatal conflict occurs, the entire vehicle system has a maximum of 60 milliseconds to detect the fault, react, and force the powertrain into a safe state. 60 milliseconds. That's literally a blink of an eye. That is the ticking clock between a safe drive and a total catastrophic hardware meltdown. So, what if the absolute worst happens and communication completely drops while you're flying down the highway? How does it fail gracefully inside that tiny 60 millisecond window? Well, the system executes what's called a stepwise active short circuit. First, it triggers a two-phase short circuit, which acts as a very brief mechanical buffer. It waits exactly 1.5 milliseconds, and then boom, it drops the hammer, engaging a three-phase lower switch active short circuit. This is brilliant because it intentionally traps all that massive regenerative energy inside the motor's copper windings instead of sending it back to the battery, securely clamping the voltage to under 720 volts. It completely eliminates the risk of an uncontrolled reverse overcharge. Section 3, DFMEA, Key Design Prevention. Time to build the hardware fortress. Remember how we said timing delays and asynchronous clocks could cause those scary communication drops? To proactively block that, hardware engineers enforce an unbelievably rigid physical design. The main processor and the external communication chips are forced to share the exact same low-jitter hardware clock source right on the circuit board. They limit the phase error to half a degree or less. It's extreme synchronization, but it ensures that data updates never lag and bits never ever skip. But the hardware fortress definitely doesn't stop there. To fight off that massive electromagnetic noise we touched on earlier, engineers spec out isolation chips with a transient immunity of over 100 kilovolts per microsecond, and they back that up with common mode chokes that damp high-frequency interference by over 40 decibels. To prevent those false voltage readings caused by heat, they drop in highly stable Class 1 COG capacitors. And to fix the magnetic distortion in the motors, they standardize 2D dynamic mapping models that adapt on the fly. It's honestly amazing. Every single failure path is methodically blocked by a highly specific hardware or software design choice. Section 4, PFMEA, Key Process Controls. How we automate manufacturing perfection. So, out on the assembly line, the name of the game is microscopic integrity. Take the soldering of the processor and those communication chips. The manufacturing line enforces a total voiding rate limit of 5% or less for all solder joints, with no single void allowed to be larger than 1%. Think about that. If there is even a tiny, microscopic pocket of air under that microchip, thermal fatigue could literally cause it to crack miles down the road, completely severing the communication line to the BMS. To guarantee that level of perfection, the physical gatekeepers have to be highly automated. Every single board goes through 100% 3D, X-ray, or acoustic scanning just to hunt down those hidden solder voids. At the end of the line, dynamic testing forces a fake torque request just to prove that the system can actually throttle down in under 10 milliseconds. Even the bolts connecting the massive power lines are phosphate-coated and tightened by smart servo screwdrivers monitoring the exact torque angle. This makes sure the contact resistance stays below an ultra-low 5 microohms. Basically, it means the voltage readings are always going to be dead accurate. Section 5, DVPNR, Production Validation. This is where we test against the extremes. The validation gauntlet for this stuff is just brutal. First, the system is spun up to a screaming 12,000 RPMs, while engineers actively bombard the communication network with massive EMI. They demand the system smoothly derate power without a single false alarm. Next, it's subjected to violent 3-axis random vibrations while cycling between -40 and 125 degrees Celsius for 500 hours straight. And through all of that, they cannot have a single signal drop lasting longer than 1 microsecond. Finally, using hardware-in-the-loop test benches, they intentionally sever the high voltage during a massive power surge just to prove, beyond a shadow of a doubt, that the system can react within that critical 60 millisecond FTTI window and clamp the voltage safely. And that brings us to the core of what we've uncovered in today's explainer. We've seen exactly how tiny electromagnetic waves, weird software timing quirks, and literally microscopic solder voids can threaten to unleash massive, destructive physical forces. But on the flip side, we've also seen the incredible multi-layered fortress of hardware, software, and manufacturing controls that are specifically engineered to keep that power perfectly contained. So I want to leave you with this thought. If our entire electric future relies on harnessing immense, potentially dangerous physical power, how do we keep innovating to guarantee that this invisible engineering shield never breaks? Thanks for joining me on this deep dive, and keep questioning the incredible technology that moves us forward.